Algebra 2, Illustrative Math, Algebra 2, Unit 4, Lesson 12 is called the number e. So you might be saying the number e. E is a letter, not a number. But e is kind of like pi. It represents a number. So our goal today is I know that e is an irrational constant, kind of like pi. It has a value of about 2.718. Okay, so pi is a Greek letter, and it's 3.14159, and it keeps on going. Now, where does pi come from? Pi comes from, you take any circle. We know that circle is equal to pi times diameter. So if I wanted to find pi, we know that if you take any circle, measure the circumference, and divide by the diameter that you measured, that's going to give you pi. Pi equals the circumference over diameter. So you should have learned in geometry what pi is. It's, measure the circle circumference, divide by the circle diameter, that'll give you pi. So E is this 2.718. And really, it keeps on going. And it comes from this formula. It's the limit, which you've probably never seen this notation before. The limit as n approaches infinity of 1 plus 1 over n to the n. So what it basically means is you just keep on plugging in numbers for n. They get bigger and bigger and bigger and approach infinity. So you keep plugging in giant numbers for n. Your value is gonna get real close to e. Okay, so the bigger the number of n that you plug in, the farther down you get for your decimal places. You get it more and more accurate the bigger the value is that you plug in there. Okay, so let's just say n. Let me just pick a big number. Let's say n equals 1,000. Okay, well, if I plug it in here, 1 plus 1 over 1,000 to the 1,000 power. I'm going to type that into my calculator here. 1 plus 1/1000th, and then I take that and I raise it to the 1,000th, and I get 2.716923. So as you look here, we got the first 3 digits pretty accurate, but then these were a little bit off. So you'd have to keep picking bigger numbers for n. Maybe I pick, instead of 1,000, maybe I add a 0 on here, maybe make it 10,000. Okay, and your value is going to keep getting closer and closer to that 2.718, which is what E is. So that's where E comes from. We're going to play around with that a little bit today. All right, so here's our warm-up. Match each equation to a situation it represents. Be prepared to explain how you know not all equations have a match. All right, so let's look at one. Scientist begins an experiment with 400 bacteria in a petri dish. Population doubles every 10 hours. The function gives number of bacteria, t hours since the experiment begins. So this one would be start with 400. That's your initial value. You're doubling, so your base is 2, and it's every 10 hours. So it's t over 10. Let me make that a little bit easier to read. Okay, so that one would be, which one would that be? This one, 0.1 is the same as, really it's like 1/10 t. Like if I wrote 1/10 t, it's the same as t over 10, and it's the same as 0.1 t. So this one would be k of t. All right, patient takes 400 milligrams of medicine. Amount of medicine in her bloodstream decreases by 25% every 10 hours. You start with 400. Now, if you decrease by 25%, that means you're going to have 75% less or left. So really 100% minus 25%. That's where I get the 75% remaining. So it's going to be times 0.75, and it's every 10 hours. It's t over 10. So that's this one, the h of t. So I'll tell you what, I'll just plug it in. And again, t over 10 is the same as 0.1 t. All right, the half-life of a radioactive element is 10 years. There are 400 grams of the element in a sample when it is first studied. Function gives the amount of the element remaining t years later. So 400 times 1/2, and since your half-life is 10, it's t over 10 or 0.1 t. So that one here is f of t. And then last one, start out with 400 for your population. It grows by 25%. So it's 100% plus 25%, 125%. So that's your growth factor, 1.25. And every decade, so since it's every decade, every 10 years it doubles, we want t to represent years, it's, t divided by 10 or 0.1 t. So that one ends up being the g of t. Okay. All right, so notice and wonder. A spot of mold is found on a basement wall. Its area is about 10 square centimeters. Here are 3 representations of a function that models how the mold is growing. So they gave us this function, they gave us a table, and they gave us a graph. So what do you notice? What do you wonder? So I kind of ruined the surprise here. You would probably say, I wonder for sure what constant value E is equal to. I already told you it's 2.718. Sorry. I would say I notice from the graph and the table that our growth factor must be greater than 1 because it is getting bigger. So that tells us E is probably greater than 1. What else? I could probably find my growth factor here because, this is my initial value, the 10. And then what did I multiply 10 by to get 27? So you're thinking, oh, okay, times what? I'm going to call it b because it's y equals a times b to the x. So 10 times b will get me to 27. So if I divide, I get, oh, okay, b looks like it's 2.7. If I do it here, 27 times b equals 74 divided by 27. I'm going to get b equals 2.74. If I go here, 201. So I'm basically just going to divide it 201 divided by 74. That'll give me my b, 2.716. So what I'm noticing here is I got the 2.7. I got the 2.74. So I'm noticing that my E must be like a crazy decimal because it ends up getting rounded to different values each time when you come here. So I would also say notice that values must be rounded because we do not get the exact same growth factor each time, which is really E. So yeah, there we go. A lot of stuff there. I would also notice that E is 2.7 something. Okay, we're not fully accurate, but we started doing some division there. All right, here's some functions. For each function, describe in words the outputs for very tiny positive values of x and for very large values of x. So what I'm going to do is I'm going to do for tiny values of x, I'm going to say for tiny I'm going to use 0.0001, and for large I'm going to use like 100,000. Okay, so what I'm going to do is I'm going to say tiny large. I'm going to plug them in. So 1 to the 0.0001. Type in your calculator. 1 to the 0.0001. Still 1. Same thing when I plug in 100,000. Still 1. Negative x. So these are for x. So this is going to be negative 0.0001. It's going to be negative 100,000. So 1 divided by 0.0001 would give me 10,000. And 1 divided by 100,000 would give me 100,000. 1 over x to the x. So this is going to be 1. If you want me to write, this starts getting a little bit harder. I can't do it in my head. So 1 over 0.0001, and then take that to the 0.0001. So I do 1 divided by 0.0001, hit enter, and then take it to the 0.0001, and it gives me 1.00092. And then I go over here. This is 1 over 100,000 to the 100,000th. So this gave me 0. All right, so then I do these one. Now this is actually your formula for E, okay? So if I plug in 1, I'll come down here, plus 1 over 0.0001 to the 0.0001, and then same thing here, 1 plus 1 over 100,000 to the 100,000th. Let's see what we get. So remember, and I gave you the formula at the beginning, as n approaches infinity. So as n gets bigger and bigger. So this one right here, this is going to actually be, this value right here is going to be my E. So it's an approximate because you can never get exact. So let's go ahead and do each of these. 1 plus 1 over 0.0001 to the 0.0001. This again gives me like a 1.00092. And then here, 1 plus 1 over 100,000. And then I take that to the 100,000. Sure enough, I get 2.718.268. So I'm starting to get E, and if I want to get more accurate, I'd change this value here from 100,000 to like a million, or like, 10 million or something like that. All right, so now E, you could use your E button on your calculator. You should have an E button. So pause the video and find your E button if you need to. So this is going to be E to the 0.0001. So E 0.0001. Again, it's kind of the same thing, 1.0001. And it keeps on going. E to the 100,000. That's going to be a giant number here because remember, we're going to basically take 2.718 to the 100,000th. So I hit E to the 100,000 and it actually gives me an error. So I'm just going to write huge number. Depending on if you use a calculator online, sometimes those can go out a little bit further. All right, 1 plus x, that's 1.0001. And this is 101,000. Okay, so just a little bit of work plugging things in. The big one here is this formula, and it says x keeps getting bigger and bigger and bigger. We want that, gives me the E value. All right, so remember that E is approximately 2.718. What does the function g have to do with the number E? So go back there, g. As I plug in larger and larger values, we get closer and closer to E. What do you notice about the relationship between h and k for very small positive values of x? So h and k, very small. So h and k. Looks like they're the same because very small values, that'd be in tiny values, be in this column. Looks like they're the same. All right, how is E like pi? It is an irrational number, which is a non-terminating, non-repeating decimal. I would say it comes from a formula, kind of like pi does. All right, how is it different than pi? I would say it's different number. It does not apply to circles. Or, well, I guess maybe a little bit of geometry, maybe not. Just say it doesn't apply to circles. All right, in the moldy wall problem, we saw the mold growth represented with, that's wrong. It should be E to the T power. So let me write that out here. Was A of T equals 10 times E to the T, where T is time in weeks and A of T is the mold area covered. How would you describe how fast the mold was growing to someone who doesn't know about E? I would say our growth factor of E is approximately 2.718. So the mold, the area of the mold is being multiplied by 2.718 every week. All right, so goal, I know that E is an irrational constant like pi that has a value of about 2.718. Record something you learned about E. So I would say E is approximately 2.718. E is an irrational number. And then I would say the formula to get E is 1 plus 1 over x to the x. And I would say you could put that notation, the limit as x approaches infinity. Or you could just say, if you didn't want to do that, you could say this is approximately E, and I would just put a note here, continue choosing larger and larger values for x to get more decimals of E. Okay, now I think my original formula maybe used n instead of x, but as long as those match up, then we're good. All right. If you need a definition of E, you can pause the video, write this down. There it is. And I think that's it. So hopefully you enjoyed this video. Thanks for watching, and we'll see you next time.